So welcome to the great debate, as we've called it, on big data. Who am I? My name's Will Lang. I'm from the Met Office. I'm one of the chief operational meteorologist team there. And why are we discussing big data? Why is that the subject of this panel session? Well, the main reason is that we thought it wasn't being discussed enough amongst the meteorological community. But having said that, it's been refreshing actually seeing a lot of the presentations this week in that a number of them have alluded to big data themes, big data issues. And I think most of us are starting to develop a vague idea about big data. But I think as a community, the meteorological community, we are unsure about what it means for us. Is it something we should be excited about? Is it something we should be worried about? Is it all hype? Or are we underestimating it? Is it, as one of our panel members who shall remain unnamed, a load of bollocks? Sorry for the language there. Do we need to be worried about it? Do we need to plan our response as a community, as a whole? Or will the benefits just flow, happen automatically? We know big data is about rapid expansion, the amount of information, the range and quality of different sources, and the way that we tie that all together as well, the way that we sift information, the way that we combine that information to get new information from those different sources. For us, it not only means greater proliferation of traditional meteorological data, such as observations and NWP, but we're also starting to look much more about things like impact information and the behaviors of societies and individuals. And all of that is now being factored into some of our forecast information. I think that making use of all that gives us huge opportunities in meteorology, but also brings some huge challenges. And the bit that worries me most is this. When it comes to high-impact weather, meteorology has a human face. Many speakers this week have acknowledged the importance of serving decision-makers in high-impact weather. And as a chief operational meteorologist, I am one of those decision-makers. I issue warnings upon which actions are taken on a national scale. But sometimes, I'll admit that on a busy weather day, when it matters most, I can struggle to cope with the amount of information that's available. There's really too much, and it can be difficult to see the signal from the noise. That worries me personally, but I suspect I'm not alone in this, and I think it's something that we should address as a community. We need to develop new ways to draw together and extract information from big data. And I think it means really searching for a whole new paradigm for how weather forecasting will work in the future. And I think that's something we should approach together over the coming years. So the way that this session will be structured, I'll get out of the way shortly, and most of the session will be about hearing from and asking some challenging questions of a panel of experts. I'll introduce them later. But to set the scene, we have, I've mentioned before, some excellent poster presentations at the back there. We have a poster presentation about crowdsourced, a database of localized high-impact weather events across Spain. And also, we have a study from our colleagues in the Basque Met Agency talking about incorporating new data sources into the forecast process. So that's all really interesting stuff. If you haven't looked at those already, I'm sure Delia and Santiago will be around to answer questions, and hopefully they'll participate in the debate as well. But we also have an opening oral presentation, which I think will set the scene very nicely, some of the issues that we'll be looking at later on in the next hour or so. So firstly, I'd like to invite Art Overeem from Wageningen University in KMI in the Netherlands to tell us about using smartphone data to monitor temperature. Art, over to you.
Thank you for the introduction. Don't worry, be excited. Let's start positive. Yes, thank you. So I will talk about urban air temperature estimation from smartphone battery temperatures. I would also like to mention my co-authors. First of all, Janja Pape, who did his bachelor thesis at KNMI. And he did a lot of work, particularly the results for Sao Paulo were made by him. Hidde Leijns from KNMI, James Robinson from Open Signal, Remco Uilenhoed and Gert-Jan Steneveld from Wageningen University, and Bertolt Horn from MIT. So we'll first give a short introduction how to estimate air temperatures using smartphones. Then I will introduce the heat transfer model we use to obtain daily averaged air temperatures. And it will show you results for different cities, for instance, Sao Paulo, London, and the Netherlands. Then I will present a discussion and will end with a number of conclusions and an outlook. First of all, crowdsourcing using smartphones can be done using an application called Open Signal. It's a free application, and it actually is not designed to monitor environmental variables, but it monitors the signal strength of wireless networks. But it also stores the battery temperature of the smartphone. And these battery temperatures can be used to obtain air temperatures, to get an estimate of the air temperature. And therefore we derived a simple heat transfer model, assuming that the smartphone is close to the user's body and that the thermal energy which is generated by the smartphone is in equilibrium with the body and with the environment. And the basic principle is that the conductive heat flow between two systems is, or at least it uses that law, that the conductive heat flow between two systems is proportional to the temperature difference between systems. And here we neglect convection and radiation. External heat sources such as the sun are neglected. And the basic principle is that the smartphone's temperature and so the battery temperature will be influenced by the temperature, by the environmental temperature. So if the smartphone is outdoors, then the outer temperature will influence the smartphone, which is a reasonable assumption. The question is, of course, does it work? So we obtained data from, in our 2013 study, we obtained data from 8 different cities. For instance, Sao Paulo, but also some European cities, Paris and Rome. And here you see our heat transfer model. Well, basically it's just a simple regression model where we use the the battery temperatures from an entire city for a particular day. We average those readings, and then we try to get an estimate of the air temperature for that particular day, for that particular city. And the model has 2 coefficients, T0, which is actually based on data from all these 8 cities, and this coefficient M is optimized for each city and each season separately. So it's a very simple model. And this shows you an example, some results for London, where we obtained the battery temperature readings for one particular season. As you can see, there are many of them. And this graph shows time series of the daily average temperature. First of all, in orange, the averaged daily battery temperature after applying a number of selections. And the solid black line shows you the daily average air temperature from the weather station, WMO station at City Airport. And as you can see in this particular case, there's a good correspondence between both signals in terms of the correlation, in terms of the dynamics of the signal. So we use this information, the battery temperature readings, to obtain an estimate of air temperature. In this case, we have a calibration data set, a validation data set, and the first day is calibration, the third day is calibration, the fifth day, etc. Not the most optimal way, so I will show results later on where we use 1 year for calibration and 1 year for validation, which is better. Nevertheless, as you can see that in general there is quite a good correspondence between the daily averaged estimated temperatures from the smartphones and the observed air temperatures from the weather station. Sometimes this does not work. This is an example for Moscow. We see this as there is a large transition in the air temperature. A change in seasons from summer, autumn to winter. And it's a land climate, so you have a large range of observed air temperatures. But for this entire period, we just estimate one coefficient. So it has to deal with this range of temperatures. And as you can see, it is certainly not able to cope with this. So we get a kind of average temperature over the entire period, but we cannot get accurate estimates for the higher temperatures and for the lower temperatures. So this is an example that sometimes it does not work. This shows you the overall results for those 8 cities I showed you. So for 2 different seasons and 8 from the weather station. So in general, there is quite a good correspondence with a high squared correlation coefficient, for instance. And now we apply this methodology to another city, well, actually to a longer data set from this city. So we obtained about 2 years of data for Sao Paulo. And more importantly, this data set is much larger. Well, perhaps it's not big data, but we have about 15,000 readings per day, which are used to estimate the daily average air temperature, which is about 10 times as high as the number of readings we had for our previous study, where we had 8 cities. Then a typical number is 1,500. So what we did here is we used data from 1 year for calibration purposes, and then we applied the algorithm to an independent data set, so an entire year, where the solid line again denotes the observed daily average air temperature at the weather station, and the blue line is the estimated air temperature from the smartphone. We also did this exercise by making a selection by only using data from a particular type of smartphone, the Samsung GTI series. So here we use less measurements, but the smartphones will be quite similar. So in terms of the used battery, for instance, I can imagine that certain smartphones have larger screen sizes and will, for instance, heat up more than other smartphones. So these smartphones may be assumed to be quite similar. And then you see that results even slightly improve. This is another example. So actually this is the previous figure, but then we added another data set, the ERA interim data set. Well, as you can see, when you look at these metrics in general, the smartphones can't beat the ERA reanalysis. However, probably the weather station data were also incorporated in the ERA analysis. So hopefully that's the reason, or not, but depending on what you like. Then finally some other results. Because we have many readings for this particular city, that also gives us the opportunity to look, for instance, at the diurnal cycle, at the variation from hour to hour. So what we did here, we used a 3-month data set, where the first part was used for calibration, where each hour, so for instance from 1 to 0 and from 1 to 2, had a separate coefficient m. So we find an optimal coefficient for each hour, and then we applied it to the second part, the validation data set. And you see that, well, on the one hand, it more or less captures the diurnal variation. On the other hand, you also see that there are clear differences between the estimates and between the observed air temperatures. And, well, if you would criticize this, you could say, well, this period is from the same season, the calibration data set, so is this, well, you should actually do this on an independent year, I guess, but At least there is a signal in this. There seems to be that the diurnal cycle can be captured to some extent using the smartphone app. And final results, some results from the Netherlands, where we plotted one metric, the squared correlation coefficient, so the correspondence between estimated and observed air temperatures, daily temperatures, versus the averaged length, the average number of readings for a particular city. So even if you have only 100 to 200 readings, you can already get a, perhaps useful, at least more or less accurate estimate of air temperature. But you would need many more to study, for instance, variations in space or in time. However, many things can be questioned. I realize that, so I want to just give a number of, I will just provide a short discussion. First of all, we think that this method works because you have many readings, and averaging is applied over the entire data set, and still there is a signal, because many readings will be indoors, but also many readings will be outdoors. And apparently after averaging there is still a signal in the smartphone battery readings. So that's probably the reason that it works. Of course, a smartphone is often not in a pocket, for instance. And a very important question is, what does this air temperature represent? I mean, here we say we have daily average air temperatures for a city, but the weather station data are only from one location in our case. The smartphone battery readings are from many locations in the city, but these locations will not be representative of the city. So that's of course a very important, very important point. And also the number of readings varies during the day. For instance, during nighttime you have less readings. And you may also have less outdoor readings in case of cold periods. The accuracy of the reading, so roughly 40% of the battery temperature readings should be known within 300 meters, but it really depends if GPS is activated, for instance. And there are many more things can be discussed. So you have 1 hour or so to do that. So some conclusions. Well, we have shown that you can get fairly accurate daily average temperature estimates for a city, and that crowdsourcing using smartphones can be promising. Well, at least that's what we claim. That's to be discussed. And, I kind of see those battery temperatures as an interesting illustration. So I think it's really worth it to further investigate it. But I particularly think that it's useful to use other sensors from smartphones, because new smartphone models sometimes have air pressure sensors or air humidity sensors or air temperature sensors. Also, they're able to detect if it's sunny or not. So I think that's more important because it's a more direct way of measuring. And of course, crowdsourcing is much broader than only using smartphones. Some recommendations, of course, apply to more cities and use more data, but also, for instance, to use urban meteorological networks, so then you can get a better validation of the temperature estimates, and hopefully, in case of sufficient readings, also a spatial validation. But in the end, you would like to have an air temperature map. Remove indoor readings. Well, for instance, use the light sensor of a phone if these data would be available. And then some outlook. Well, first of all, about 20% of the land surface of the Earth is covered by the mobile phone network. So that means that in principle you could use of course your phone, but in general I suppose also your smartphone. And there are hundreds of millions of Android smartphones, for instance. So that means you have many. You could potentially obtain many observations from these smartphones. And you actually have free transmission of data. Well, not free for the user, but free for the researcher or the operational community maybe in the end. I think that the smartphone and the application has not been designed for air temperature estimation. And this shows you another app from the same company called Weather Signal, where they display the air humidity and, for instance, the air pressure observations taken from smartphone sensors. So this is really for people who are not really interested in the network strength, but really interested in the weather, and they can contribute. But the number of observations from this app seems to be much larger than the number of observations from the Open Signal app, because that's more general. People want to know what is the signal strength of the network. They find it apparently more important than weather. So, well, thank you for your attention. Here are some references.
Thanks, Art. That's very interesting, and it's just one of the interpretations, I guess, of big data, things like crowdsourcing and smartphone data. I suggest we keep most of the big questions to the end, but are there any quick specific questions now? Santiago?
What are the differences between outdoor and indoor temperature and the problems with that? What are the problems with that? Do you understand the question?
Yes, yeah, of course, users can be at the outside at the 10th floor of a building. Differences as well. So that's not taken into account. I think there is some information on the vertical component, but I also believe that this information from GPS is relatively inaccurate in the vertical.
Okay, I think we're going to move on, actually. So thank you very much, Art, and stick around for the rest of the conversation, please. So we're going to move on to presentations from the panelists now, and I'd like to introduce the first of our esteemed panel of experts, is Robert Moreau. He's head of research at Meteor Group, which he's asked me to remind us all is the largest commercial provider in Europe. Prior to that, he was based at KNMI in the Netherlands, and for a long period at ECAM WF as well. So I'll hand over to Robert.
Thank you for calling me. Thank you for calling me an expert. Don't think I really am, but I probably can challenge a few, provoke a few questions here. Yeah, big data. Just an introductory talk with a few provocative statements. When you start to read about big data, first of all you discover that there's not really a clear definition. That puzzles you a bit. And here's some definitions that you will find in the literature. The top one is the one that's probably the shortest one. It's really about conversion of unstructured data into information. So the definition is big data is about something. And so it's really unstructured, like the telephone data of art. It's really, they're all over the place. They're even moving around. And you convert it into information. The other more elaborate way is that it's a new way of processing. I'm too tall. It's a new way of processing non-conventional data in addition to existing data. So non-meteorological, messy, unstructured. Messy is also the word that you use. It's not the football player in this case. It's messy. The data is really messy, is really a lot of noise in it. And still there's information there. And it will improve maybe your weather forecast on the decision-making process of our clients in the commercial world. And your clients even in the civil services. And it is also combining many different sources of data. It's really about combining everything. Consumer behavior, what people buy, what people do, plus the weather. Weather is maybe just one component. It's everything. It's about everything. Messy is important because it's really about that. You should think of a radar picture where you look at a radar with lots of clutter. And it's about really filtering out the right information of that radar picture. Now, an experienced forecaster can look at a picture like that and see and make sense of it. You don't really have to declutter it a lot for him. So even he's in fact worried if you declutter too much. And that's what this data set is all about. You really have to cope. You have to learn to cope with all this kind of information and noisy information that's in there. So there's two types, The classic thinking is a high resolution, more data. So you have data in gardens, cars, power plants perhaps, on roads. You have road sensors. And also cars are interesting. Meteor Group is part of a big EU project where we try to get information from cars. Car manufacturers give us data. They send data real time, and we try to infer data from where cars brake, because it tells you the ABS is hit. Then you can is triggered. Then you can tell maybe it was slippery there. So you can derive a climatology of slipperiness there, things like that. And it is also about indirect data. So really infer information from things like what Art is doing, from battery temperatures, but also other things like Twitter, Facebook, human behavior. If a lot of people are on the beach and they communicate to each other and they say it's nice weather here, it is nice weather there. Maybe you can do something with that. So it works two ways. So you can try to find a relationship from the weather to the behavior, like in retail. You have a weather forecast, you have weather information, and you can maybe deduce how much beer people will buy and drink. It's interesting, people want to know, because beer companies want to know that as well. But the other way around as well, you can maybe infer from behavior information about the weather. It's a challenge. It's difficult, but it's a challenge. And that's something that in the big data world, people think like that. They want to do that. What are the applications? That's a difficult one. Perhaps nowcasting, really for roads, slipperiness. You can communicate between cars. Energy, warnings. You can issue warnings. Where is the severe weather now? So you can help the forecast, because it can tell you where the thunderstorms are now and how quickly are they moving, not moving the right way. They might be moving a different way than you think. You can definitely use it in retail. You can refine maybe the information on consumer behavior. Maybe you can derive high-resolution climatology. You get more information, very, very local. And there's a lot of these back garden, weather stations. And we can do what I call, that's my favorite, forensic meteorology. So when you have a storm, when it's a thunderstorm has been, and you go out and you want to see what has happened, very often the local fire brigades have already cut up all the trees and removed the trees, so you don't know really what happened, because you can really see a lot from what has happened there by the way the trees are oriented and so forth on the ground. So that's something you can also quickly see. Just a sidestep. Weakness in meteorology. That's a good one. Classic thinking. We think it's only a lot of data. I get a lot of people that say, I have lots of experience with big data. I work with a lot of data. No, not really. That's part of it, but I challenge everybody with that. But it is really about more than that. It's getting more information out of different types of data. We don't have a lot of knowledge of new correlation techniques. The big data world, they say they have a lot of new techniques with clustering. They really build relationship between this part of the world and that part of the world. And we may not be aware of that. I have no idea, to be honest. That's why I'm not calling myself an expert. But I'm really curious to see what those techniques are. The why versus what. That means that in big data world, people are not really interested in why there's a correlation. Now, you're all scientists. We're all scientists, as we are here. That really insults us a lot. But that's how you can think. If the correlation is there, and it is true, you think it's a significant correlation, you should be able to do something with it and not wonder too much about the why. And there's the scientific arrogance. Wow, it takes one to know one. So we have been doing this already for many, many years. Come on, it's station observations. You convert it into an analysis. We draw nice maps. That's unstructured data into structured data. And now modern data assimilation. You convert unstructured data into a regular analysis. MOS is post-processing, data assimilation, retail things. We have been doing that for many, many years. Analog methods, NAO statistics, correlation between an ENSO and the rainfall somewhere in Europe. Nobody knows exactly how it works, but we think there's some kind of correlation there. Maybe we can make a forecast based on that. But yeah, we have numerical models. So we are way ahead of the rest, I think, because it's difficult if you derive techniques to make forecasts better with big data. I think it will be difficult to beat a numerical model. So only for the short range, that's my statement. And the threat, well, maybe. Meteorology might not be needed anymore. If these telephone companies, they find a way to derive temperatures, they can do without us. And they also can infer precipitation information from telephone signals and weakening telephone signals. So Well, what else? They can build their own radar. It might be too messy for meteor purposes. So I don't think we'll ever be able to make a good medium-range forecast based on big data. That's far too noisy. You need a bloody good data assimilation system to filter out all that noise. But for the short range, I think it's possible. And you can, of course, find nonsense correlations. So you have to be very careful. If you test various different kind of relationships, you can find 10,000 different relationships. There'll always be one that will score at whatever percentage significance level. That's it. Thank you very much.
Thank you, Robert. So we'll all be out of a job soon, according to him. I think taking a different slant on things will be our next speaker. And I'd like to introduce Ken Milne. Ken is head of NWP at the Met Office, but he has a background in both research and forecasting. And for many, many years, he was the leader of our ensemble forecasting team and also our weather impacts team as well. A very appropriate area to be involved in this kind of discussion. Ken.
Thank you very much, Will. I'm not quite as tall as Robert. I'll bring this down again. So yes, I'm going to try and give a little bit of a Met Service perspective on this, but also just at the end a little bit from my WMO role as well. So I might start from what Robert termed as part of the arrogant part of we've always done this. The Met Services have been for many, many years, decades, handling increasingly large volumes of data. And the graph at the top here shows how our volumes of data that we ingest into the Met Office have grown over the years. And note that this is a logarithmic scale, so we're up to getting close to hundreds of thousands of megabytes of data per day. But that is a simplification, as Robert said, of what big data is all about. Will said in his introduction, as a forecaster, he's often overwhelmed by the sheer amounts of data that approach him. Oops, sorry. This is a slide that I pinched from Gavin Robbins, who spoke yesterday, or the day before, on Monday, from the Flood Forecasting Centre in Exeter, but just looking at some of the vast range of different types of inputs that come into the forecaster, whether it's be a hydrologist or a meteorologist, every day, which you have to... and ensembles, which they have, all giving them different bits of information. So huge amounts of data that they have to cope with. Just looking at what we do in the Met Office in terms of our modeling strategy, we run a global modeling system which runs a 20-kilometer grid over the whole globe, so that itself is vast amounts of data, and then of course it outputs lots of different variables, and we run it in an ensemble, so there's lots of different runs in the ensemble, running several times a day. That then provides boundary conditions for a regional ensemble running at 1.5 kilometer resolution, again with an ensemble. Incredible amounts of detailed information in here, all producing ensemble information. So they are just from the NWP systems, huge amounts of information. We bring all that together into an ensemble system to give a picture of the uncertainty. And so the forecaster is faced just trying to do a forecast for 1 hour in the day with all this wealth of information covering what might happen and uncertainties and things. So as a community of scientists helping to support them, we started to try and do things to try and distill that information, to help them to get stuff out of it. So on the right here, we see a picture which has actually gone through quite a sophisticated process of post-processing of this ensemble to try and distill it into a more sensible picture of the probabilities, the risks associated with heavy rain in this particular case. So that's a first example of how we're trying to sort of address the issue of distilling this vast amounts of information that forecasters have to deal with. We produce visualizations for them, and here, something that our forecasters can look at online, a combination on the right of the latest high-resolution model run from the deterministic model, along with probabilities from the ensemble, animating together. So again, helping them to distill all this wealth of information into a picture of what the weather might look like, along with the risks and things associated with it. So trying to pull this together into sort of information that they need to turn things into a forecast and warnings of risks. Then we've got all this data that's coming out, and this is just looking at the forecast. We've also got observations and all that sort of vast amounts of observations and things as well, but just thinking at the forecasts. Supposing that one of the sort of things we might be asked is, what's the weather going to be like in Exeter at noon tomorrow? So we could pull out information for that, and we get a picture. Well, actually, we do that for lots of different sites across the southwest of England, even more sites across the southwest of England, right across Europe, right across the globe. So suddenly you can see the vast amounts of data that start coming out. And then we do this for a great long list of different variables and diagnostics of different aspects of the weather. We also do special application variables. For example, we've got winds up here, obviously, but we also do particularly hub height winds for wind energy and all sorts of other diagnostics for specific applications. We take all this and we turn it into information on probabilities, percentiles, information that breaks down the risks and things. Out of all this, at any one time, our system might be holding something like a bit over 1 billion pieces of forecast information at any one time. So we are used to dealing with vast quantities of data. But as Robert says, there's more to big data than that. This is just another example of how we might, and there have been many, many examples shown in this conference this week and in previous conferences, but just to highlight an example of how we can take all this wealth of information and try and turn it into something that's relevant to decision making. And so in this case, we've heard a lot about severe weather warnings. This is a tool designed to support the Met Office National Severe Weather Warning Service by using the ensemble and the risk matrix that we use to distill a first guess of a severe weather warning ready to go into this format as a warning. So there's a lot of work going on and things like this to try and help the forecaster and ultimately the end user by distilling all this type of information into useful forms. This morning, Becky Hemingway in my team gave a talk on the vehicle overturning model, where we're trying to go a step further and estimate a risk by combining a hazard, which is the wind speed in this case, with information on vulnerability and exposure. So here now we're pulling in other data sets from other types of sources, quite separate from meteorology. We're bringing in data from social sciences, from things like spatial information on where people are, or in this case, where road networks are, and the characteristics of these roads to understand what's the likely impact of this strong wind hazard on the road network and turn it into a risk of disruption to society due to accidents on the road caused by the wind. And then, in the second part of her talk, Becky was talking about how she verifies this. And so she's using other sorts of information, like road traffic accident reports, to try and verify these forecasts and determine what the real impact of this weather was. So this is quite a nice example of how we're pulling together weather information, the vast amounts of ensemble data that I was talking about, with other sources of data to create something that's useful for decision making for society. So we're getting further from just original meteorology and into the use of big data. One of the challenges that we have as a National Met Service is that we're trying to make all this forecast data and things available to as many people as possible to use it. But every time we get a new supercomputer, and we've just got one, we're just taking delivery of a new Cray supercomputer, and over the next year or two, we're going to be increasing the resolution of our models and producing bigger ensembles, producing more and more data out of it than we have in the past. Now, if we just throw all that data out to our users who want to use, people like Robert's team at Meteor Group, who want to use this data, they have to change all their systems if we give them just as it is. So we're trying to look at ways to better manage and handle this data so that people can use it. So we're moving away from just giving away the data in the form directly that it comes out of the model on the model grids, which is what we would call a level 0 sort of data. We're starting to reserve that really just for research purposes and for direct coupling to other models on the supercomputer only. And moving towards producing data on standard grids and over standard domains, what we would just call level 1 data. We're not changing the fundamental contents of the data, but we're just putting it into standard formats so that everybody can use it. And when we change our system, Robert's team don't have to change theirs so they can exploit it. So this will be how we plan to wholesale data in the future. And part of our process of trying to make the handling of this data easier. Above that, we do further things with it. We do some post-processing where we might do some bias correction or adjustments according to make corrections for local topography and that sort of thing. And then finally, we produce forecasts where we actually combine outputs from a variety of different models, perhaps from nowcasts, from short-range, high-resolution models, and then from longer-range, lower-resolution ensembles, into producing blended forecasts which give us some sort of optimized combination of a best forecast, and make that available as well, again, in the standard formats that people can use and aren't susceptible to changes that we might make. And then we can present those in a variety of standard formats, such as fields which represent end products, or map layers, which is a nice way that people can take that data, that wealth of data, and display it in a standard mapping system that anybody could use and make it more accessible for people to use. Data for specific forecast sites, just as images. So to finish up with, Will introduced me mentioning also my role within WMO. And WMO has a big interest in looking at the sort of thing I've just been talking about, actually, the ways that we can make sure we get data out to those who want to use it, get it to a lot of different countries' Met services so that they can make use of data. And one of the things that I do in my WMO role is I chair the steering group for a project called the Severe Weather Forecasting Demonstration Project, which is designed to try and help support some of the Met services in least developed countries who have very limited resources in terms of access to forecast data and that sort of thing, to give them access to enough data to be able to produce basic weather warning capabilities in their countries to save life and property. And there's a whole network of stuff around this, like providing adequate training and how to use it and that sort of thing. But one of the key things here is each project is based around a regional center which provides guidance products on severe weather risk for the next few days within their region. This is an example from the Southern Africa project. And they produce a website which provides all this information. They take data, They take data from global centers such as ECMWF and the Met Office and use that to provide their guidance and pass it on. Data that I've been describing earlier would be their computer systems, their internet bandwidth and things would be completely swamped and overwhelmed by it. So everything that we produce for this project is done in the form of PNG images so that they can download it over simple, low bandwidth internet connections. And so this is another example of how we can help to distill this vast amount of information and get it out to end users so that they can use it for the real job that we're all here for, of protecting life and property. So just to finish with, I've just put up a number of discussion points which might help to trigger some thoughts for where we go with the discussion. There's a number of aspects to big data, I think. There's things that we've always done, there's things that are changing, and there's lots and lots of opportunities for the future. In some ways, and by some of the definitions that Robert gave, meteorology already does big data. We produce and process vast quantities of data every day. The data volumes and the range of types are a real challenge to forecasters, to users, and to systems, technical systems. And I've mentioned a few of the sort of things that we're trying to do to keep that manageable and to help to distill information. So we produce on summary products. We do first guess tools. We're trying to do this data decouple the data that we provide out from the forms of the models that we run them in to make them more manageable and provide them in constant and standard formats. We're also doing a lot of work on improving the metadata, the archiving and the searching facilities so that people can actually access the data they want. Some of the big opportunities and challenges are the use of non-met data, the sort of things that we were hearing about in Art's talk and that Robert was talking about, use of new observations, new types of observations, which are non-conventional ones, crowdsourced and social media data, the coupling of our meteorological data to other forms of data, such as geospatial data, such as vulnerability fields that we can use for risk assessment and that sort of thing, and other sorts of user data for many applications. So some ideas there to try and help stimulate some discussions, which I think often much consistent with what Robert said. I just point you to one thing that might also be of interest, which is at WMO's Congress back in June this year, Congress 17, this paper number 9.1, which I've checked today and is still on the website, was a WMO paper on big data and covers a lot of these ideas and talks about different definitions of what you might call big data and things. So if you're interested, that's a useful reference too. Thank you very much.
Thank you, Ken. Next up is Tim Hewson. Tim's from ECMWF, where he's the principal scientist in the forecasting section, responsible for quality control of the operational models and also forecast product development. Before that, he worked for the Met Office, where he had a dual role as a research scientist, but also as a chief forecaster. Tim?
Okay, thank you, Will, and good afternoon, everyone. This will be slightly shorter than Ken's presentation. I'm trying to stick to my 5 to 10 minute brief. I think Ken had a slightly longer brief by accident. So, I'm giving an NWP type perspective from ECMWF. The range of things that ECMWF does is like that, and the range of the things that the Met Office does is quite a lot bigger, I think. So just bear that in mind. Big data, well, in an operational context, there's big data at all stages of the process of developing numerical model forecasts. We've got the input observations, huge amounts of unstructured data, as Ken was mentioning. That goes into the numerical models, massive amounts of number crunching, huge data volumes. Actually handling that in the future will be an incredibly big challenge for all the sensors around the world as the resolution of these global models gets bigger and bigger. And we've got 4 new staff at ECMWF working on that very project now. That then goes into the output forecast fields. This is where we're getting towards the forecasters. And then those fields, which are arguably unstructured in the sense that they don't actually consist of things that forecasters can make direct use of. Those are then converted into products, so charts with pressure on, as we'll see in a minute. Products for forecasters and for forecasting. There's a kind of sense in which some of these go directly to the customer as well. And then finally, we've got the users, the customers, the really important people in the whole chain that actually act on the investments that we've made in these processes earlier in the chain. So. Responsibilities, ECMWF and the National Met Services have responsibilities in this sort of area here. ECMWF's role, by mandate from the member states that fund us stops here, but then the National Met Services and the commercial are the more direct link with the forecast users. So I'm going to focus on that red arrow here, and just because I'm kind of responsible for forecast products development at ECMWF and the products that go out, I'm going to focus on that and just give you some little examples just to kind of highlight the amount of data that really does get post-processed, and that we are actually doing, I think, overall quite a good job in this big data world with producing products which people can understand. So we focus on that. So my first example is just a very, very simple example. This is a metric for the slides that follow. This is obviously one data point, the forecast for midday tomorrow in Sofia. I have no idea whether that will be right, but obviously that is not big data at all. But then let's go to the more simple products that we at ECMWF produce. Simple pressure chart, that's a day 10 forecast for yesterday, I think it was. What goes into that? Well, it's just mean sea level pressure. It's just one model run, the high resolution forecast. 10,000 data points, quite big already. We produce meteorograms, so those are site-specific forecasts. These are my back-of-the-envelope calculations. About 460,000 data points go into that. You might say that's rather a lot. Isn't this just 50 times a few days because we've got 50 ensemble members? But there's quite a lot of post-processing goes into the maximum minimum temperature. You have to scan all the values from the model run, so there's quite a lot of data goes into that. Ensemble mean of MSLP, that can look a little bit boring and bland compared to the high resolution forecast, but we've already got 1 million data points in that because there's lots of different runs. One of the things I've been involved in is post-processing the output to make it much more structured in such a way that the forecasters can relate to it directly and understand it. And so we produce what's called Dalmatian charts, which show where all the cyclonic features are, and then some aspect of the cyclonic feature here, it's the actual maximum rainfall within a given radius of the actual point in all the ensemble member. To construct that, we have about 50,000 data points. And the numbers keep going up and up and up. We have an ensemble mean here with a normalized spread, so that tells you how uncertain the forecast is relative to how uncertain the forecasts have been at that particular lead time in the last month or so. So the purple areas there are showing high spread, the green are where there's higher confidence. The numbers keep going up and up. If you keep going to the sort of monthly forecast range, 420 million data points go into this chart showing the globe. You may also notice as the data volumes are sort of going up, we seem to be getting quite a lot of, maybe some less helpful products coming out here. All the white area is basically telling you that we don't actually know what's going on. So there's a little bit of irony there. Sometimes the amount of data that you process reduces your confidence to the point where you can't actually say anything other than that we don't actually know. But anyway, go on. This is a converse example. 20 billion data points go into this chart. This is one of the pride and joy of ECMWF, a nice EFI chart showing the anomalous weather all around Europe. So you've got anomalous cold here, anomalous warm here. This signifies a jet stream. This is symptomatic of the ocean. So there's all sorts of the ocean being particularly cool at the moment. There's all sorts of bits of information in here. We've got very strong winds in this sort of area here, unusually heavy rain up here, and some other bits of signals elsewhere. So there's a huge amount of useful information. This is relatively short range. And so there's a massive amount of time and effort goes into this, because this is all based on comparing the extremes of the distributions in all the ensemble members with the extremes of the distributions in the hindcast, the reforecast that we spend a huge amount of time and effort and supercomputer power on at ECMWF. And then finally, the seasonal forecast. This is a multi-model seasonal forecast, so these are disparate data sources from 3 or 4 centres. We can construct this, and this is 130 billion. The monthly forecast before. I mean, the reason that cold anomaly is there is basically because the sea is below normal, sea temperature is below normal now, and it's likely to stay that way, and that sea temperature anomaly extends to a great deal of depth. So I could have probably just worked that out on the back of an envelope rather than investing millions and millions. And as you probably know, seasonal forecasts are not renowned over Europe for their high levels of skill. Hopefully I'm not offending anyone in the audience that thinks they are. Okay. So just a little summary. Big data, as we've seen already, is a ginormous topic. And you can just pick out little bits, and I just want to highlight 1 or 2 to sort of stimulate discussion. I think I've shown that we have, been successful. This is a good topic. We have been successful in compressing huge amounts of data from numerical models into something which is compresses and usually conveys. So certainly at Easingworth, in some of the work I've done, we can compress all the data from all the ensembles into lots and lots of little fronts, which tell you where your confidence in the frontal structures is. So this is a story of success, I think. Things which are less good, again, this is slightly not following on from the previous topic, but my impression is that customers don't always want to take advantage of all this wonderful data that we're giving them, particularly the probabilistic stuff, and that's a key point here. I think we've got a long way to go for acceptance of probabilities, and that's the theme that's come up in the debate that was on here earlier on, I think. And I do wonder with cost-loss ratios, again, economically that's very sound, but I do wonder whether customers care about cost-loss ratios, should be using more probabilities, more better use of this big data. Probabilities, I mean, we're our own worst enemies in some ways when it comes to probabilities. Let's say you look at the apps that come from National Met Service and commercial providers. It's incredibly difficult to get probabilistic information on those apps. Sometimes the probabilistic information that is there is impossible to understand because even the help pages don't tell you what it means. That's really, really bad, I think. And then you find that these sort of issues may come back to haunt us when a very severe event is missed or massively overhyped or just slightly in the wrong place. Tanya, in the previous discussion session, talked about a case in Slovenia where they got really heavy rain out by 15 kilometres, and that led to really poor reaction from their actual sort of customers. So that was quite sad, I think. But it is a question of actually conveying those probabilities and getting the customers to understand what all this big data really means. It means we cannot get things exactly right all the time. Okay. Finally, as I said before, big data does not necessarily mean better, as we saw with the monthly and the seasonal forecast. I had to carefully put the word data in there after my first version of this slide. Okay. Then the ugly, this is one of pet hate of mine again to try and stimulate some controversial discussion. Robert mentioned this, black box statistics, I hate those. This is, and the capacity to have black box statistics as we go into the world of big data becomes much, much greater, and we have to really, really guard against that. We have huge data volumes of massively disparate types, sales of certain things in certain countries and weather in other countries, etc., etc. We have fast-acting data mining tools, and in the scientific world, we have pressure to publish. You add all those together, and that can lead to identification of irrelevant connections. So I think we always have to remember, as Robert pointed out, that on average, 1 in 1 million analyses of data pairs, if you're trying to look for links, will show a correlation level which is statistically significant at the 99.9999% level. And that sounds great in the paper, but if you've done 1 million correlations and you put that in your paper, that's a very sad approach to science. Never forget the physics or the actual causal effect that underlies these relationships. So that's all I have to say. Thank you.
Thank you very much, Tim. I think I can sum up those 3 talks by saying that we've agreed, I think, that big data is big, really, really big, and also messy, very, very messy. But I'd go back to my initial questions now. Is it for us? Is it something that we should be worrying about? Should we be factoring it into our plans for the future? Is it real or is it hype? What do you think? Over to you. Who would like to start the debate? Santiago.
Thank you. I think in last presentation, big data has many flowers also. So we must not to focus on big data thinking in volume. Okay, we have many other flowers like variety, velocity, but I mean, I think that really the challenge and really the task is to focus on variety. I think that we have many possibilities from now to next year to introduce some different, a huge variety of data in processes into the meteorological business, even data that today we don't know. For me, this is the focus of big data, not really the classic point of view of volume. For me, the key question is in variety, not in volume.
So it's the messy aspect that is more of a concern than the size.
Yeah.
Would the panel like to create a comment on that? Anyone like to have a go? Robert?
I think I just agree with that. It's about the value, of course. I disagree with that. And but I think it's also about lots of data. So it's a combination of lots of different things. And then get value out of it. That's quite clear. Mm-hmm. So yeah.
I agree, but I'm sure that we have nearly solved problems or nearly solved problems deal with volume. Okay, I think many of grid meteorological agencies like you has solved many problems dealing with volume. Okay. But perhaps not. You don't focus on variety. This is good for a small meteorological service like vast meteorological service to focus on user needs, new instruments. Okay, it's not our business. Really big volume is not our business.
But the question is really what is value and what is quality.
Sure.
If you look at all the data that comes out of this the messy thing.
No, I agree.
Yeah.
Yeah.
Sorry.
Yeah, I agree variety and value and all those things are important and we have to think about the users, but I don't want people to leave here to think that the problem of dealing with huge amounts of data is solved in the world of NWP. That problem is getting, in some ways, ever worse because we're reaching the point now if we kind of get the computers more and more powerful, more and more cores and so forth, that computers cannot run because they're going to be too hot. And so we're reaching the stage, you think, okay, we'll just keep Moore's Law, we'll just keep improving the power of computers. That's not going to happen overnight. It's progressed relatively straightforwardly up to now, but there are some really big technological challenges there, and we certainly, in one interpretation of big data, we mustn't forget that side of things.
Okay, Dennis, would you like to say something about that?
Yeah, I would like to make one comment and one question. First, the comment. I don't think we should see big data as replacing the physics, but complementing the physics or our science in areas which physics cannot explore. And I think it has the ability to build the bridge between our science and the application. And for me, the main question in the end is, do we do that as meteorological services to build that bridge? Or is that bridge built from the other side and we are reduced to a pure data and not a decision solution provider? So that's also maybe a question to Ken, how you see that in the Met Office. And then a question to Ken and Tim. I think a month ago, NOAA announced that they will make available their data to large cloud platform operators like Amazon Web Services, or there are many, Microsoft, IBM, etc. So that you would transfer data only once and people could use that on their cloud platforms. Is that something you also consider at ECMWF or at the Met Office?
Okay, I'll take that second point first because I need to clarify your first question. But in terms of making data available, we are increasingly making more of our data freely available. The Met Office operates a system called DataPoint, which makes now all our site-specific data freely available for anyone to pick up and use. And we are moving towards making our gridded data more freely available as well. Some of that requires some work on the technology, which we're doing at the moment, and putting it onto the standard grids and things that I was talking about. At the moment, we still make some of that data available through a wholesaling approach, so it's not necessarily free of charge, but we are, and that's mostly about handling costs rather than any profit element, but so we are making it freely available, and that's following government policy as well. So we're moving in that direction, yes. Sorry, can you just clarify your first question again? It was about the role of...
Well, it's a bit about our role as whether we... I think meteorology is, of course, physical science, so I rather see big data as a place or a tool which we can use to when we bridge the gap between the science, so the output of the physics, and the user space. So how do human humans behave in different weather, what's the impact of a storm, those kind of things. Do you also, how do you see that? What should Met Services do?
Okay, yeah. Obviously, a core part of what Met Services does is that underpinning science and processing to produce the core underpinning NWP of products and data on which everybody's forecasts are based. That's not to say, though, that they don't also have a role in communicating that data on. I think they do. First and foremost, we have a role for communicating data to the public for health and safety purposes, for protection of life and property, as part of our National Weather Service, Public Weather Service duties. Beyond that, how much we do beyond that is a decision for individual countries and individuals, the mandates that they give the National Met Services, so I can't answer that generally. But certainly in the UK, we are mandated by running profitable services as well. So we have a role alongside the private sector in communicating for specific parts of business and industry, specific roles, which we do on a commercial basis in the same way that you do. So there are many roles, but we've talked a lot here about distilling data into impacts which affect society as a whole, and I think that is very much part of the Public Weather Service role.
Tim, would you like to comment on that?
Yeah, I'm perhaps not going to comment on the second point because you asked me to comment on the other one, which is the cloud. Well, we don't deal directly with customers that are involved in like protection of life, etc., or selling things at ECMWF. You asked about cloud computing. That is definitely a good idea. We have had a number of people come to our meetings over the last few years and request cloud computing facilities to cut down the data transfer. It's entirely reasonable. Project is on hold at the moment, temporarily, until we can find resources due to other higher priority areas, but it's certainly a direction down which we would like to go, make it easier particularly for the commercial customers. It's a question of finding the resources. So yeah, it does not mean, however, I mean the US is probably giving this data away for free. It does not mean that we'll be giving this data away for free to everyone, because we are bound by the governance of our member states, and they would not allow us to do that, certainly at the moment.
Okay, thanks, Tim. Let's move on. Who would like to ask the next question? Over there, sir.
Hi, I have a question regarding ensemble method. In that, day by day, the number of models are getting increased. So, how much is too much? When are we going to stop just increasing the number of models and pay more attention to improving the existing models, increasing the capabilities and accuracies, precision of the existing models, increase physics?
You go first?
Who would like to go first on that?
First, then I'll follow.
Yeah, that's an excellent question, and whatever answer I give, some people in the audience will probably be offended, so I apologise in advance. I think from a global altruistic point of view, there is merit in the world having a certain number of numerical models, and I think that number is probably around about again, this is where someone will criticise me, I'm sure, maybe around about the 4 or 5 level. I think you need variety in order to develop some kind of sense of competition amongst the different people. If you just had one, then it would be like a kind of communist type system. So I think we need variety, but at the same time, if we spread ourselves too thinly, then you won't really get anywhere. So I would say about 4 or 5, but I think it's an excellent question.
I wouldn't disagree too much with that. There's certainly a benefit in having a number of modelling systems, and we still see significant benefits when we look at ensemble forecasts in combining more than one ensemble together into a multi-model ensemble, which can produce overall better performance than the best individual ensemble. So there are benefits there. The other part of the question, in a sense, is how many ensemble members might you need in order to better specify your the distribution. And we do a lot of our focus with ensemble forecasting is on predicting extremes. And if you're going to predict extremes with any degree of confidence in how likely they are to occur, you do need a reasonably large number of ensemble members. I think we're in the order now of sort of 25 to 50 to 100 members, 100 members in the multi-model ensemble, 25 to 50 in individuals. And I think that's about right. I don't think we need to go massively expanding beyond that. It gives a reasonable representation of the probabilities at the level that anyone's likely to respond to them. So just on the other part of your question, let me assure you, we do put a huge amount of effort into improving our models. Any ensemble is only as good as the model that goes into it. And so I think it's probably fair to say that both ECMWF and the Met Office and probably every other NWP centre, the bulk of the effort goes into improving the physics and the numerical representations in the models.
Yeah, and the assimilation.
And the assimilation, absolutely.
No,
Okay.
Really. I don't want to be too stuck on ensemble forecasting.
That's fine. Yeah. I think it's actually too far within the comfort zone of these guys. I think we need to put them out of their comfort zone. Who would like to ask another question at the back?
When I hear the contributions that I've seen on this conference, I got the feeling that big data is very often understood as scraping smartphone data, and I think this is rather maybe not the most rational point to start. How about the more obvious things? There's a great number of people that have their private weather station. Some of them are, I admit, pretty crappy, but some of them are pretty ambitious, and they even form into sort of private observation networks, but these data are greatly ignored. I admit they might not be suitable for weather prediction, but maybe for some model output statistics, they could be quite valuable. And but apparently nobody, not from the companies and not from the weather service, invites these people. Or if you maybe together with some manufacturer, if we had maybe outside temperature sensors or rain sensors that have a cloud service, so they transmit their stuff to some cloud service, so you harvest the data and show it to the smartphone of the user. You get much for free, and I would find this much more obvious than, for example, looking at the battery temperature. If I look at people in Moscow, especially in winter, I would never have the idea that the battery temperature might be connected with the outside temperature. Well, maybe in Sao Paulo where people don't wear much clothes, but in Moscow, well, I'm sure I wouldn't have expected that to work. So are there any ideas to use this available meteorological information and not scraping such, let's say, exotic things first?
Robert.
Yeah, absolutely. Yes, I myself am part of the NetAtmo network. I have a little gadget at home in the garden measuring temperature and humidity and so forth. And I think in a few weeks' time I also have the rainfall gauge as well. It's wonderful. There's lots of local sensors in my city, and in Holland there are really thousands and maybe millions of data points. And the big question is how to and we also heard today about the WOW project at the Met Office. It's a similar kind of thing where you have the weather amateurs contributing. It's on the net. You can just go to the net, look for NetAtmo weather map or something like that, and you find. And I can give you my address, and you can see what the temperature is in my back garden. And we're using that. We want to use that. I mean, we're looking into the possibilities of using it. It is a bit of an issue because people have those things, not of course at WMO standard positions. Because sometimes in the back of the garden where the sun shines in the afternoon, and so you suddenly see this temperature go up, and there's exactly the messy type of data that I was referring to. Do you throw away that whole point, or do you make use of part of that data series, and can you still infer some information, like from a cluttered radar image? That's a whole challenge for us. And we're currently looking into the net Atmos set, and we would like to filter the data and see what we can retrieve and what we can have to throw away. But we have to think about this definition of quality, because it's a different kind of quality, and you cannot really check every individual data point anymore. So the same thing I mentioned in my talk, cars. Cars also register a lot of information these days, and you can get a lot of information from cars. Windscreen wipers helps you in determining whether it's raining or the drizzle is happening. You can think of wind turbine information, where definitely the wind measurements on the turbine, definitely if it's on the top of the thing, are not good. And you can also get information on the rotation speed, on the rotator speed. Helps you in all these things to get the forecast and the final product better. So absolutely, yeah.
Amateur observations, but for monitoring. And I guess that's the same way I would assume that I would use the smartphone data. So I wondered if we could ask Art if you'd thought of any more practical applications of things like the amateur observations or the smartphone temperature data.
Sorry, more practical issues? Yes. Yeah, well, first of all, I agree it would be very wise to use the existing stations, certain for operational applications. So, in a certain sense, I do agree. The only thing is, I think you should also investigate new sources of information, and I think that smartphones could be appropriate for that matter, because then the number of readings could be improved much more than using conventional stations. The potential is there. That's what I'm saying.
Well, can I just add a little? Just going back, Robert mentioned the Met Office WOW system, and actually, at the back of the room there is a poster from a similar system from Spain. But I go a little further, and we're not yet ingesting that data into our operational forecast systems, but we certainly are looking at how to do that. And Robert talked about the quality issues, and certainly, of course, these stations don't meet the traditional WMO standards, but that doesn't mean that they're not a lot of which can filter out ones which are clearly at odds with their neighbors and that sort of thing. But the other thing is that as we do feed it into operational systems, our data assimilation systems have an awful lot of very clever quality control within them, which will put lower weight on observations which have lower quality or have been seen to have lower quality. So there's lots of things that we can do to make use of that sort of data. So absolutely, we are looking to make good use of that.
Excellent. Would you like to add anything about the Spanish system?
Yes, thank you. Yes, maybe I would like to raise the issue of the cooperation or collaboration among weather services when dealing with big data, because yes, I have heard today about this WOW service of Met Office, and we have developed in the Spanish Weather Service our system Sinovast, and you can see in the back wall the poster presented in the poster. And news ideas about how to make the better use of this information could be shared, and even these systems that are already developed could be shared for other countries or for other weather service. Yes, our system, of course, don't mean to be an operational system for forecasters, but it can help. It can be an information easy to have a look at it, and an information rich, very fresh, and very enthusiastic from the amateur meteorologists who are always full about the weather and always sending information. Thank you.
So you're proposing that we share weather impact information as well. I think that's a very good idea, actually.
Yeah.
And the systems, yeah. Tim, would you like to say something?
Yeah, I mean, I'm 100% behind data sharing. Some of the
kind of big data, the very local data, is not so relevant to ECMF, but I would just point out that, as Stuart Goldstraw highlighted in his talk, observation talk on the very first day here, essentially we've got three sets of data. We've got the GTS type data, which is disseminated freely, and then we've got this kind of what you might call the crowdsourcing data at this end. But there's also a huge amount of data which is very well quality controlled in the middle, which tends to be kept by individual Met services for their own use, and they're not provided out to the rest of the world or sold. And that is a really big, and that's kind of high quality data. You don't need to do too much quality control with it, so I'm okay. But that's really valuable data, certainly for verification. I mean, precipitation, for example, is extremely variable in space and time. And if we want Met services to predict extreme precipitation, flash floods, etc., we really need to share some of that data a bit more. I'll just give you an example. If we look at maybe a flash flood case over Italy, we look at the rainfall observations that we have, which are fairly sparse. We might see 50 millimetres in 24 hours. You think, crikey, that's a lot. And then you check your forecast against that. And then a little bit later, someone from Italy complains and sends in all their local observations, and you find that just down the road there was 500 millimetres in 24 hours. So it's not that uncommon to be like an order of magnitude out, and so there's a really big gap to be filled there, even with the conventional observations just available within sort of individual countries, never mind the additional back of the garden obs.
But you're focusing now on the meteorological applications, but in that local data can also be a lot of useful applications for linking it to, let's say, consumer behavior, human behavior, if you look at the local space, in the local scale. So that also you can build those links, and you know exactly how people behave because of a certain temperature or precipitation. And then helps you maybe in making good forecasts or whatever for behavior. So yeah, you can use it in many ways, not just for meteorological applications, but for other things. Of course, our dream is to have one global kind of shared information database.
And the question started from, well, is this smartphone data not so useful? But actually, where that comes in and can be very useful is in filling in some of these gaps, because the smartphone users will send in information about the most extreme events. And when we start looking at trying to forecast and understand and predict impact, then that's what we need to know about. We need to know not about what's happened at the standard high quality observation sites, but what's happened at the gaps in between where the most severe impacts are. And verifying these impact forecasts is very difficult, very challenging. And things like smartphone voluntary sent in data is critically important for that.
Thanks, Ken. I'd like to get an American perspective on this, if I may. So, Sandy, have you got anything to add?
Okay. I'd like to present a little vignette and then ask a question of the panel. Our lab in Boulder, about 15 years ago, one of my scientists came and said he wanted to start a citizen weather observing program. And I think the key there was it was organized. We get data frequently every 5 minutes. And we did actually put some effort into trying to get pictures of where the data were being taken. You know, is it right next to a building or in a garden or whatever? And the vignette is that during one of the severe hurricanes that hit Florida in 2004, there were no observations. I think the surface winds were over 65 meters per second, and the only station operating was one of our citizen stations. So the Weather Service, the FAA, they were all down, but the citizen weather station was still going. I always meant to go check and see what that guy, what kind of a system he had put up. The question is, I really appreciated the definitions of big data because there's so many different ideas of what it is. And I think one of the most valuable that's going to serve us in the future, and one that we're working on in Boulder, NOAA Boulder, is more effective use of the voluminous satellite imagery that we've gotten for 50 years. And the issue there is a little bit like the intelligence services have. They know there's a few bad people moving around the system trying to get through airports and stuff, and so they have their cameras and they're looking at everybody, and then based on a correlation and other techniques trying to recognize you know, the next Osama bin Laden riding the plane. My question is there much, we're sort of launching activities in this area between some universities and us. I was wondering if there was much of this use of pattern recognition, correlation, and other techniques to identify things like convection and other key things from the imagery.
Okay, who would like to answer that?
I'll make one quick comment. Just to say that eSIMBA invests a huge amount of money and time and people in the assimilation of satellite data. I think we have full-time about 20 staff working on the simulation. And despite that, we only use about 10% of the data that is available, partly because of redundancy. So we do a lot with the data, I think, already. I accept your point that there is big scope for doing pattern recognition type work, and I think there's been a big track record of people doing that kind of thing over Africa, where other data sources are for convection analysis. We saw some talks on that today, where other data sources are severely lacking. And just to give you one insight into the pattern recognition ideas that we're perhaps looking at eSIMBA, we have problems maybe pinpointing where tropical cyclones are at time zero. Sometimes we resolve the ambiguities in satellite winds incorrectly, and so we're thinking now about, rather than maybe using the bulletin information of where the tropical cyclone is as a kind of instinctive reaction, to not do that. That's partly what the Met Office does, and I think they do that quite well. But eSIMBA, we're thinking of maybe doing image processing of satellite imagery in the vicinity of tropical cyclones to pinpoint the eye, which in principle should be straightforward, and then use that as a kind of bogus point within the assimilation scheme. So we're starting to think about those ideas.
Yeah, I think there's definitely scope for that. We recently hired a big data person in my group, and one of the first things he said that he would want to look at radar images and do some decluttering. And we had to tell him that can't say the problem was solved, but he had lots of ideas about how he wanted to do it from his computing background, to give him the chance to do it. But for the moment, no. But there's definitely more techniques out there in this big data world that can probably help us in getting better pattern recognition and getting clearer pictures of satellites and radar images. I'm quite sure there will be a contribution from that world, I'm convinced.
Okay.
Yeah, and I can give you a couple of other examples. We still, I believe, assimilate a number of cloud track winds and things into the systems, which is a rather old, actually, application of that sort of thing. But more recently, since the Icelandic volcano eruption, which disrupted air traffic control so much, a huge amount of investment has gone into better identification of volcanic ash plumes from satellite, which is not straightforward. Cloud, you've got to see it where it's mixed with cloud. But by using some of the many different channels of data that we get out of the satellites now, a lot of algorithms have been developed which are able to do that sort of thing. So that's a sort of pattern recognition and scientific diagnosis out of the vast amounts of information available. And the other one I'd mention is that there are some new techniques being developed for recognition of incipient early developing thunderstorms. To develop them to recognize them as early as possible in their formation for nowcasting. So there's a number of things going on.
Okay, thanks. The gentleman at the back had his hand up. Is it a comment or a new question? Sorry?
A new question.
Yeah.
And when thinking of big data, maybe a suggestion. I see great potential not maybe to deduce meteorological parameters from the telephone data or whatever, but behavioral data about the users. And we must not forget, we are the experts here, so for us it's a very usable weather forecast if we know the temperature, humidity and stuff. But an end user, who we learned this earlier today, has a quite limited concentration span, who in the end he wants to know, for example, is it a good evening to have a barbecue? So if we can maybe deduce from the data, this is an evening where people in, for example, Frankfurt have typically a barbecue, and we can predict the ability to take a barbecue and maybe the clock or the humidity, so we can offer as a service to the user that what he actually wants to decide. Do I take the bicycle? Do I take the raincoat with me?
You're touching privacy issues there, but can I answer that question? Because that's a very interesting point. It can even go further than that, because if I know what kind of person you are, what your health is, what your background is, what you have done in the past few hours, I can probably really make a very personalized forecast for you, whether you have to take your medication, what the impact is on the heat forecast, because now we learned that yesterday as well. When they have this heat indices, they're global, they're kind of universal, uniform heat indices. But if I know who you are, I can tell you, you will be bothered by the heat forecast or the issue, and you can live on with it, and you're quite happy to live through that. So it makes it very personal. But if you go into the big data world, there are big forum discussions, bigger than this, on privacy issues. So, and I think so far meteorology has been not touched by that. But if we go that way, then we have a privacy issue, because then I know exactly who you are.
It's not necessarily personalized. Just if you
well, I like to do
that you have a big number of people or of telephones being in this park where you usually have a barbecue. Then, it's not personal at all.
No, it's also, but also when you're on the beach and people buy ice cream and so forth, you can anticipate that kind of behavior, and you can infer information about the weather. Absolutely, but I mean the next step is that you go even further and you make the personalized forecast.
I think that's the logical conclusion, Robert. That's where you'd go. And I think there's a huge ethical dimension to all of this that we could be talking for hours about. Gentlemen, there, one final comment, perhaps.
Okay. Well, I think big data can be very useful in the future if we are able to link it to new approaches, innovative approaches in order to forecast weather and to real interdisciplinary thinking. The big data we should create in order to improve our forecasting shouldn't be only based on meteorological information, but on biological information. Imagine I could forecast if tomorrow is going to rain looking at the bees' behavior. Or why not? Or considering social networks and counting words, or looking at different disciplines. So the success of any big data is going to be linked to real interdisciplinarity in relation to global environmental change. That's my point of view. The question is, do you know any meteorological service that has incorporated some factors in the forecasting that are not just meteorological factors?
Not particularly. I know that people are looking at car data and so, but you wanted to say something?
Well, I can make a general point. I'm not sure that we'll be looking at the behaviour of bees to forecast the weather tomorrow, and we have very sophisticated models based on physics and maths, etc. But you are right in the sense that we do have to work in some multidisciplinary way, and at ECAM we're getting together with a chemist now. In a big way, it's clear that chemistry can have quite a big impact on the weather. Biology will become increasingly relevant. At the moment, for example, we have something called a leaf air index, which affects the evaporation in tiles across the world, and at the moment that leaf air index varies seasonally, but you can imagine that it really should vary according to the prevailing climatic conditions. Another thing which we see regular errors in our forecasts associated with is irrigation. So in the Nile Delta we have problems with our forecast there because irrigation leads to evaporation, keeps the temperatures down. So that's like a human activity which we would like to incorporate. Cities are in many models, they're not in the European Centre model. That's another area, that's a human impact. So this is definitely becoming multidisciplinary. The ECAM strategy for the next 10 years includes a lot of kind of earth system science, which is all these disciplines coming more and more and more together. And so your general point I do agree with, and it's the way to go.
Ken?
And yes, I absolutely agree with all of that. The forecast, the underpinning forecast, I think absolutely should remain rooted in physics and the methods that we've been following. But where the other types of data really come in are in this whole business of translating that physical forecast into a societal forecast and how it's going to impact on society. And there's a huge, we've started a little bit of that. Some of the sort of things we were talking today about how we have impact-related warnings and that sort of thing. But there's an awful lot further we can go in that.
I think that takes us back full circle to Dennis's original question about should we exploit non-standard connections and things outside traditional physics and meteorology, and I think it may become inevitable to a degree. I think we've run out of time as well, which means that the time has flown by. It seems like there's been a very fruitful discussion and lots to talk about and lots to think about for the future, I think. If I can try and sum up two main points as far as I'm concerned. We've come at the problem from two different directions, I think. There's the size of big data, and we've talked about ways where we can sort, simplify large data sets, billions of information points, and try and distill it into one signal. And that's a challenge for us all, and it will continue to be a challenge as models grow and the number of products grow almost geometrically, I think, in the coming years. So that's one approach. And also the other thing is these new sources of data, crowdsourced data, smartphone data, other non-standard correlations, connections of things. And I also think we have a responsibility to explore and exploit those new sources of data and also share them as well. So again, that's something that's come out loud and clear, I think, from this meeting. I hope you've enjoyed it. I'd like to thank the panel for their time and their contributions. So thanks very much to Ken, to Robert, and to Tim. Can we give them a round of applause, please?
And let's have a big data session next year with lots of presentations.
Let's do it again. See you then. Thank you.
Good discussion.